Okay, topic 5.4 is uniform circular motion. Now, so this is for objects moving in a circle. So it has to be a perfect circle, or we'll assume perfect circles, or parts of perfect circles, moving at the same speed, but moving around the circle. So it seems pretty simple, and it's not too bad, but the one thing is that's always going on for objects traveling at a constant speed around a circle is that they're constantly changing direction. And if you're constantly changing direction, then you're constantly accelerating. So even though your speed stays the same, your velocity is not the same, and your change in velocity um, leads to an acceleration. So the velocity of an object in a circle is always tangential to the circle, while the acceleration and the force are directed radially inward. So if you have an acceleration, you must have a force. And since they're directed inward, inward seeking or center seeking is centripetal. So we call those centripetal forces. So let's take a circle like so, and let's consider the velocity of an object at one point, tangential to the circle like so. Now, at another point, say here, we keep that as well, same length, but v2 is like that. So it's off differently. Now let's think of these vectors in terms of the change in v. Because change in v, you remember, is v2 minus v1. So minus v1 would be, so this is also like this. You can think of it as the sum of v2 plus minus v1 like that. So v1 minus would be like this. It would look like that, minus v1. So if you add those two vectors, v2 plus a minus v1, like so, then here is your delta v, like so. And you notice it's center seeking towards the center of the circle. And that would happen anywhere you were to draw a v2 minus v1 on the circle. So that means that A, which is delta v over delta t, is center seeking centripetal acceleration, or centripetal acceleration. And we call that A with a little c for centripetal acceleration. There it also has a centripetal force associated with it. Fc is the centripetal force, and that's also center seeking in the direction of the acceleration. And Fc equals the mass times AC. In fact, centripetal forces do not exist in themselves. The center seeking force is the net force of the system. So that means it's always made up of other forces. Let's take a simple car going around a circle. In that case, the car is constantly changing, and you might even hear it squealing. You know, if it's going fast enough, you'd hear the squealing of the tires. In that case, the net force on the car, F perpendicular and Fg, if it's a flat circle, just cancel each other out. And the net force is due to the friction of the tires. And that friction would be directed inward, and that friction would be the centripetal force. Okay? And we'll do a lot of examples for you to see this. So it ends up that the sum of your forces equals the centripetal force is equal to the mass times the centripetal acceleration. And we use our free body diagrams to decide what force or combination of forces create this net force. Okay. So FC equals M times AC. So, but for circular motion, going around a circle, it turns out that the acceleration is equal to V squared over R. So if you look at the units of that, you'd have meters squared over seconds squared over the radius of the circle, which is meters per second squared, which makes sense for acceleration. So acceleration is V squared over R. And where R is the radius of the circle and V is the speed of the object. Now let's think of V for a second, because V for the circle, you would go around, if you took the distance to go around once, well, that's the circumference. We call the time it takes to go around the circle a period, okay? The period to go around that circle. And the circumference is 2 pi times the r, and the period is a capital T because it's a specific time, the time to go once around the circle, the time to do a lap, okay? So now we have these formulas for V, AC, and FC. And FC is our net force, which we get from the sum of the forces from our free body diagram. So let's look at an example problem. Say we have a car, a horizontal circle, sorry. Swinging a ball perfectly around on a frictionless surface horizontally. So it would just look like something like this. Okay? And we could, if it was completely, you could just go in air as well, so that you would have FG down, and that would be balanced by F perpendicular exactly upwards. And then what's bringing it inward is this tension force right here in the string. So in that case, the sum of the forces equals mass times acceleration. And the sum of the forces is just Ft, okay? The tension. Well, let's suppose we're given some data. The mass of the ball is 3 kilograms. The radius is 1.5 meters. The period of rotation is 1.2 seconds. So let's find V, AC, and FC. Well, I know my formula for velocity is 2 pi r over t. And I know AC is V squared over r. And then I know FC equals FT equals M times AC. So the velocity, or the speed actually, is just, because we're not really, it's the speed going around the circle at any point. 2 pi times the radius, 1.5 meters, over our period of 1.2 seconds. So 2 times pi times 1.5 divided by 1.2 gives 7.85 meters per second. So AC would be v squared over r, or 7.85 meters per second squared over 1.5 meters. Or 41.1 meters per second squared. And then Ft, which equals Fc, equals m times AC, and the mass is 3 kilograms times 41.1 meters per second squared, so 123.3 newtons for our centripetal force, which happens to be, in this case, the tension in the cable, or the rope, or the string. How about a vertical circle one? So we'll do a vertical circle, and this time we'll use the same values for our mass, acceleration, or mass, radius, and period. Okay. So but in this case we're spinning it around vertically. So the ball out here, up here, down here. In these cases, it depends on where it is, because in each you'll have different free body diagrams. Okay. When it's at the bottom here, you have Fg down, you have tension up, but those Ft up minus Fg still has to equal the sum of the forces Fc. Okay? In the middle here, your Fg is down, Ft is directed inward. Well, it has to be slightly, some sort of arrangement to give you the directed, well, Ft and Fg have to be at slight angles to each other to give you the net force going in like this, directly towards the center. The sum of those forces as vectors would have to give you a center-directed force of Fc. That's kind of tricky. And then the top here, in fact, in this case we have Fg in the same direction as Ft, but they still have to add together to give you the sum of the forces of Fc. So in this case, it would be Fg plus Ft equals Fc. Okay? So, could be, you can see how your tension in the string would change as it goes around, to very little at the top to the most at the bottom. So, however, even though that's the case, you still have the same, to keep the same speed going around, which is 2 pi r over t, that would remain the same as before. It would be 2 pi times 1.5 meters over 1.2 seconds. It would still be 7.85 meters per second. So the speed is staying the same as it goes around. And the acceleration, the centripetal acceleration, would be v squared over r. And that's staying the same. It's 41.1 meters per second squared, which means the sum of the forces, which is Fc, is still m times ac, which would still be the mass of 3 kilograms times 41.4, or 41.1 meters per second squared, 123.3 newtons. These values stay the same. They don't change. They're based on the speed you're going around the circle and the mass. So, but if we take, like, at the bottom of the circle here, in this case, we see we have an Ft minus Fg, which would be 30 newtons, right? 3 times 10, was it 3 kilograms? Yeah. Would equal Fc, which is 123.3 newtons. So Ft would be 123.3 plus 30. 153.3 newtons. So the tension down at the bottom is 123.3 newtons. At the top, you would have the sum of the forces is Fg plus Ft, and so our 123.3 newtons would equal 30 newtons plus tension. So in that case, the tension is only 93.3 newtons. And near the middle, the vector sum of Fg plus tension would equal 123.3 newtons, directed towards the inner part. So that would be approaching the 123. So it's at the most at the bottom, 153, at least at the top at 93 newtons. We'll do more problems like that because I understand that's pretty complicated. How about a car on a flat road? So if we just have a car on a flat road, like so, going around with its wheels towards the center of a circle. So the circle would be coming out of the page, back into the page like that. Let's say this car had a mass of 1,000 kilograms, a mu of 1.2, coefficient of friction, a speed of 22 meters per second, and could we come up with the R for that? Well, the free body diagram for the car would be FG down and F perpendicular up, and friction would be directing that towards the center. So the sum of the forces equals the friction, and that's our FC, which equals our mass times AC. And the friction force is mu times F perpendicular times the mass times AC. So mu is 1.2, F perpendicular is FG, FG, actually, you see how this relates to acceleration is mu times g, because Fg is mg. You can see that the masses cancel out. So the centripetal acceleration is 1.2 times 10 meters per second squared, or 12 meters per second squared. So if that's our centripetal acceleration, now we could put that into the equation for it. V squared over r, because we were also told the velocity was 22. So 12 meters per second squared equals 22 meters per second squared over r. Bring up the r, divide by 12. R will be 22 squared divided by 12, or 40.3 meters. Okay. I think I'll stop there. I got a couple other problems, but I'm going to do them on a separate video to not make this too long.